Hello everyone. Today we will see Introduction to VLSI. VLSI is also called as Very Large Scale Integration. In today's lecture we will discuss what is VLSI, VLSI applications, VLSI industries and the syllabus of VLSI. So let us first understand what is VLSI. So in the content of VLSI, we will see its preview, VLSI world, Moore's law, VLSI industries, objective for VLSI design, applications, future of VLSI. Let us see to the image. You can see it is a 5 MB hard drive being shipped. This image is of 1956 and the hard drive is of IBM company. So here we can see a 5 MB hard drive was so huge at that time in 1956. Now in today's world you can see that in 1956 in this image you can see the 5 MB hard disk was so much huge and the cost was about $10,000 per 1 MB. And in today's world, here you can see this is a 4 TB hard disk, 4 terabyte hard disk, and which is actually smaller or to the size equal to passport. This is the image of 2013. So this is the power of VLSI. This is called as VLSI advancement. So we have compressed the device in such a handy thing. First in 1950s this was so huge and now it is so small. So this is the highlight of how the VLSI have changed the technology. ENIAC, the first electronic computer. In this image you can see how big the computer was. It was around one big huge room, and in which there were many electrical transistor devices, and through which the computer thing were operated. And here you can see around 2 to 3 operators into the image who were operating the computers. This image is of 1946. So this was the huge part of the technology which was in the past. The technology was very difficult to handle. It was so huge, and the operators required were like around 2 to 3 operators, and again the space required for all this small memory computers, we need a large amount of space. So this was the past in 1946. But what VLSI have given us? So here you can see Charles Babbage designed the first computer starting in 1823. So see the image of first computer here, and now the today's computer, how small they are, so handy, and we can take them anywhere. So what VLSI have done, VLSI have compressed the technology. It has taken to the like sort of taking everything, every hardware to the nanotechnology level, and hence the technology now is portable. It can be carried with in your pockets. It can be when you are traveling, you can carry the technology with you. The best example is your smartphones, your laptops, and your hard drives, your pen drives. So this is how the technology has been developed, and this technology is due to VLSI. It is called as Very Large Scale Integration. So unbelievable facts. AVI-DAC was the first digital computer at Argonne National Laboratory and began operating in 1953. It was built by Physics Division for $25,000. The picture shown AVI-DAC is a pioneer organic computer science Jean F. Hall. AVI-DAC stands for Argonne Vision of Institute of Digital Automatic Computer, and was based on architecture developed by mathematician John von Neumann. I guess many people or students have been heard about John von Neumann. Again, you will see this name in embedded systems. So, but just basically understanding the fact is that this is how the computer was being operated, and this is how huge the computers were in 1953. Let us see the Apple development. So first Apple computer was seen like this. It was bulky, it was huge from the present things. And here the iMac, here you can see in 2011 how the iMac was the slimmest and the shortest computer and one of the fastest computer in the world. So this is the development via VLSI. So let us understand about what is VLSI, very large scale integration. From the past images, from the present image which I have shown you, you might have understood that the technology which we were operating was based on the transistors, and the transistors were electrical transistors, and it were huge, and many people and large space was required to operate these things. So what VLSI have done is it has compressed the things, okay, and it has compressed with a huge amount. The difference between the present technology and the past technology, here you can see the difference. It is like a huge difference, right? So this is what is the power of VLSI. So in VLSI, basically what we are trying to learn is that how we can make the hard drives, how we can make the PCBs, how we can make the ICs basically small, and how we design it. Okay, so this is how we are going to learn about in this subject, like how we will design the things, what will be happening into the VLSI details, and etc. So first let us understand how large is very large. So SSI, small scale integration. Here 7400 series 10 to 100 transistors were there. So it is called a small scale integration. Only 10 to 100 transistors are present into an IC. Then medium scale. In medium scale, this is 74000 series, 100 to 1000 transistors were there. LSI, that is large scale integration, in which 1000 to 10,000 transistors are there. And now the subject VLSI, very large scale integration. Here more than 10,000 transistors are present at a time into a PCB or in an IC. So this is the power of VLSI. And ULSI and SLSI, these are not presently so popular, and presently you need to not understand about all these things. So let us stop of understanding VLSI. So basically understanding that in an IC there are more than 1000 transistors present into a small IC, and how this has been done. This is done by very large scale integration. So I'm just giving you the highlight of the subject. So there are MOS, metal oxide semiconductor, and transistors. So CMOS are complementary metal oxide semiconductors. Design circuits using MOS and CMOS. So detail in the further lectures we will see how the circuits are designed and how the ICs are designed using MOS and CMOS. So basically what we are looking here is that the transistors are developed by the technology using MOS and CMOS. So here we need to understand in this subject is understanding MOS transistor operation, its design equation, etc. Understanding parasitic and perform simple calculations. So obviously we need to calculate the things whenever we are designing something in very small area. Next, understanding static and dynamic CMOS logic. Obviously we need to understand transistors at a CMOS level, and CMOS level is at just I'll give you highlight that it is about a very nano level. Next is estimate delay of CMOS gates, networks and long wires. Estimate power consumption. So obviously power consumption also is a very big important parameter, okay. And understanding design and operation of latches and flip-flops. Now basically let me tell you, in the second year everybody has studied digital electronics. So you might have also done the practicals of digital electronics, where you have seen the ICs of digital electronics. But those ICs were I'll say again you might have handled those ICs and they were small. But when we are learning these ICs, gates, networks in VLSI, these ICs are so damn small that you won't be that won't be easily visible, or you just can feel a small area in your hand. So this is what is the power of VLSI. So we are learning digital electronics like gates, networks, latches, etc., but at a nano level, designing it at a nano level, and that is called as MOS and CMOS transistors. We will see in further lectures. Just I am giving you highlight here. So this is a chip, IC chip. Now here you can see there might be number of transistors, gates, flip-flops, etc. So, okay, in this particular area, so that this IC is getting operated. Now hope you have gotten highlight about what is happening in VLSI. In VLSI, the computers were very large, and now we have brought it to the nano level. I'll say it at nano or microelectronics level, and now we are designing these ICs at a very small size. So this is the technology we are learning in this subject. I hope everybody is getting what I'm trying to tell you. Now this is the Moore's law. We will not go into detail because in the further lectures we will see in the detail. Just here you need to understand is that every 18 months the number of transistor doubles. So like here you can see this is the timeline. Okay, this is the transistors per diameter. So in one, like in for example in 1 centimeter, how many memory or how many processors and how many transistors would be there. And here you can see that as the time is going on, the area is getting small, and the number of transistors and memories and microprocessors are the size of the microprocessor is getting small, and the memory is getting increased during the years. Okay, so this is how the technology has been growing. I'll repeat in Moore's law. Just you need to understand is that the memory of the microprocessor have been increased. Here you can see the red line of the memory, and the area of the microprocessor has been decreased. Okay, so in the smaller area, maximum memory has been stored. Now I'll give you one example. Just imagine in your SIM card, how much is your memory? It might be in KBs, but in the future I'm telling you that you will not need any memory card or something, because gigabytes of memory will be available in your SIM card, in your mobile SIM card only. Okay, so this is how the technology will grow. The area will become small, and the memory wise it will become huge. So this is all about Moore's law. So this is the timeline. Okay, so just you can see that in nanometers. Okay, this area is in nanometers, and how many transistors are there. Okay, so these are the years. Okay, here 2.6 million, and around in 16 nanometer of area, around 19 say around 19 millions of transistors might be present into that certain area. So this is all about the timeline. Okay, so area is getting small and memory is getting increased, or the transistors in that area is getting increased. Timeline of electronic devices. Now here you can see how the VLSI have changed the world. Nowadays, like 2000 to 2016, sensors, transducers integrated on SoC. So SoC is system on chips. So in this image you can see system on chips. Okay, so first you can see the transistors were like this. So in the recent workshop we saw that LM35, so it was of same type. Okay, so this is the transistor. In 1950s IC became like this. In 1960 to 70 the processors were like this. You know everyone about Intel. Then you can see in 1970 to 80s the SoC became, and this is how the chips were. In 1980s and 19s you can see FPGA and ASCIIs. Now a field programmable gate array and etc. we will see in detail in much more things. Just I want to show you that the transistors from this size has again decreased, and the size now and today it is not visible. You might need a microscope to see them, right? In certain SoCs, system on chips. Okay, so this is how the nanotechnology is growing, and we are designing it in a very large scale integration. Integration means in a very large scale we are integrating. We are assembling small parts into we are assembling many parts into a very small area. This is called as very large scale integration. Next, okay, so here you can see during the years the power has been increased and the area has been decreased. Okay, so the area in which the materials or the gates are been installed has been decreased, and the power of these devices have been increased. Okay, now see, now here you can understand, in 20 nanometer transistor you can fit around 250 billion of them in a silicon wafer around the size of a fingernail. So this is the chip today, this is the transistors, number of like 250 billion of transistors in this particular area. iPad Air 2 has a custom ARM core CPU and custom octa-core PowerFX GPU for a total of 3 billion transistor on a die. So imagine your headphones, your AirPods, your iPads have this sort of transistors into them, which are like which is smaller than the nail of your finger. So this is how the size of VLSI chip is. And okay, and in the past years you have seen how big the technology was, and now you can see how the technology has been growing. Okay, so cost of VLSI chips. Now let us understand the costing. Okay, so 3 billion transistors and it's pricing around 40,000. Okay, Indian rupees 20. Again, just let us understand one MOS transistors. Okay, so one MOS transistor nowadays, again let me understand, let me give you the highlight is that in this thing what we are trying to understand is that the price is also getting cheaper. Okay, this as per the size, in some things the price might go higher because in the processors and some things. Okay, and in some conditions or in some single operations the costing might also be at smaller things. Now costing has many layers. Let us don't go into the costing right now. Later on we will understand about the costing. Just understand, obviously the technology is growing, hence for the time being the costing is present and then it degrades according to the time. So cost is something which I think we should not discuss at the moment. Let us move ahead. So factors considering in VLSI design. So VLSI integration improves size, speed, power. So these are increased. Okay, and obviously the cost is improved. Okay, improved means size to the cost has been improved. Might be in 1950s and etc. the cost might be very high present to the present conditions. So integration reduce manufacturing cost. Obviously whenever you are manufacturing something small, so the costing reduces, and you can always make some things in bulk, so that always the cost reduces. Okay, and again the assemblies are not manual, rather it's computerized, because the transistors are such at nano level and billions of transistors are present into that. So now let us understand VLSI domain: circuit design, programming and analysis, tools used to design circuits and layouts, and IC manufacturing. So here you can see design, CAD tools, technology and VLSI. So again VLSI is such a hardware sort of thing. Okay, so here you can see in design, circuit design, programming and analysis is required in designing part. Tools to design circuits and layouts. So here we need to use some tools which will design VLSI, and again there is a technology, IC manufacturing. So hence VLSI is distributed in these three factors. You need to design circuits, you need to program these circuits, and you need to again do analysis of these circuits. Okay, so you need tools again for design and the circuit layouts, and then the final thing is the technology, it manufactures the IC. So this is how the VLSI domain is. So companies, VLSI companies in India mostly. So Analog Devices India Product Development Center, Bitmapper, ControlNet India, Dellsoft, Infochips, EDA India, Horizon Semiconductors, Microchip, Motorola India, etc. So syllabus, again let us go on to our syllabus. What we're trying to tell is, so quickly coming on to the syllabus of VLSI design. Okay, here you can see again 80 marks examination, 3 hours paper, okay, and 20 marks class test. So again we have seen about all the objectives in the earlier PPTs. Now from the next lecture we will start unit 1, that is introduction to VHDL and design. So how the circuits are been designed we will understand in this unit. In unit 2 we will find the fault tolerance and testability. So basically we will understand how to test a circuit and how to find its tolerance. In unit 3 we will understand CMOS. It is one of the very important chapters, okay, because in the PPT also we saw we need to understand CMOS transistors. In unit 4 we will see non-ideal current and voltage effects. Okay, so what are the current and voltage effects of a transistor? When we design some transistor, what are its current, voltage and power factors, we will understand in this chapter. In unit 5 we will understand CMOS design. In unit 6 we will understand the fabrication and layout. So CMOS design is all about how we can maintain the ratio, how we can adjust number of gates into the certain designs. And unit 4 fabrication and layout, ultimately like giving the fabrication and layout of all the circuits which we are designing. So these are the main things we are learning into this subject. Again these are the textbooks which we have mentioned. Okay, the main addition is like McGraw-Hill. It is one of the famous books which you can always follow, and I think this would be the only book I'll suggest which is easily available, and you will get every possible things into that book. Okay, again VLSI design black book is also one of the good books which you can always learn from. None of the book is bad, I would say, but I'm just trying to tell you the easily available books into the libraries. Okay, so again these are the reference books, you can go through it. So from in the further next lectures we will try to understand the introduction of VHDL and design of digital circuits. I hope you understood the today's lecture and introduction of VLSI. Thank you.